Let's continue the ZAERO Advanced Training, Section 5, Theoretical Background of Discrete Gust Analysis. The aviation regulations define the design discrete gust profile in a deterministic manner and continuous gust profile in a stochastic manner. Now, usually discrete gust loads tend to be more critical for aircraft with low wing loading, and therefore they are likely conservative compared to the continuous gust loads. The FAR 25 retains the 1 minus cosine discrete gust criteria in addition to continuous gust. And now the equations of motion of the aeroelastic system subjected to a discrete gust can be formulated by adding a generalized aerodynamic force due to the gust term on the right-hand side of equation 1.1, which we saw before. So in equation 5.1, this new gust term is right here, where QHG of IK is the gust column, and then WG here is the gust profile. So when you take WG divided by V, that gives you the induced angle of attack from the gust. Now, since the Fourier transform will be used extensively in the gust analysis, its definition is first shown as follows. First, in equation 5.2, the Fourier transform of f of t can be expressed here, where we have capital F of I omega is given by this integral. And the inverse of the Fourier transform of f of I omega is given in equation 5.3. So we can recover back the time signal f of t through this integral of f of I omega. Next, we'll look at the generation of a gust column. The local angle of attack is given by alpha of t equals wg of tau over v, where tau equals t minus xg naught over v, and xg naught here is the gust reference point. Now the frequency domain counterpart of this alpha of t is alpha of I omega, which equals wg of I omega over v times e to the minus I omega times x minus xg naught over v. And this e to the minus I omega times x minus xg naught over v is the frequency domain counterpart of a traveling Dirac delta function. So next we define a generalized aerodynamic gust column QHG of IK, given in equation 5.4. So we have the AIC matrix pre-multiplied by the spline matrix and the modal matrix, and then post-multiplied by this phi g of IK. And phi g of IK is given in equation 5.5, where we have these terms, and one example of this term is this minus nz times e to the minus I omega x minus xg naught over v. So this is the gust acting on each aerodynamic panel of the aerodynamic model. Now the frequency domain generalized aerodynamic forces due to the gust profile wg of I omega is given in equation 5.6. So we have phi h transpose times fg of I omega is the dynamic pressure Q infinity times the QHG of IK times wg of I omega over v. Now this generalized aerodynamic forces due to the gust term is the term that appears on the right-hand side of equation 5.1 to account for the gust excitation. We have three approaches for the discrete gust analysis in ZAERO. The first approach is the time domain simulations directly from the state space model. Now this needs the rational approximation of the unsteady aerodynamics, but we do have potential problems due to the spiral gust column terms. But it does have advantages in subsequent control design. In fact, it's the only method available of the three that you can use for the subsequent control design. For example, to design a gust load alleviation control law. Next, we have the frequency domain analysis using the Fourier and inverse Fourier transforms. So now the open loop state space model with frequency dependent aero matrices. We have a state space representation of the control system with constant coefficients. However, this method needs careful treatment of the rigid body modes. And this method is what we would consider the exact analysis because the aerodynamics are solved in the frequency domain. And then lastly, we have the hybrid approach. In this approach, we have modal gust excitation via the Fourier and inverse Fourier transforms, and so therefore there's no need for the gust column rational approximation, and the number of modal gust inputs are equal to the number of normal modes used in the analysis. So in the hybrid approach, the gust aerodynamics are solved in the frequency domain, and the rest of the model is solved in the time domain. So first, let's start out with the state space time domain equations of motion. Here, the gusts are assumed to be span-wise uniform in the following formulation. However, span-wise corrections can be made in ZAERO to the gust columns to reflect non-uniform distributions. Now, the resulting Laplace domain approximation of QHH is QHH, QHC, and QHG. So our QH tilde of S, it's the approximated QH, is given by this equation 5.6, which we've seen before in previous sections, but now our A0, A1, and A2 matrices and our E matrix have this additional term associated with the gust aerodynamics, AHGI and EG. Now, to avoid coefficients associated with the second time derivative of the gust velocity, approximation constraints must be applied to the gust columns to yield AHG2 equals 0. So when you do the RFA on the gust columns, we highly recommend to specify constraints on your gust columns such that the AH matrix corresponding to the gust columns are set to 0. ZAERO does not do this automatically. You must specify this in the input. Now, augmenting the aerodynamic state vector XA, remember XA is our lag terms, now has this additional EG term for the gust, and now the resulting time domain open loop equation is given in 5.8. So we have x dot AE is AAE times XAE plus BAE UAE. These first two terms are just the aeroelastic plant model, which we've seen before, and now we add on some new B columns, B terms, BAW times W tilde G. So continuing, the new coefficient matrices in equation 5.8 are given here in 5.9. W tilde sub G is WG and W dot G, and then our BAW is given by this matrix. Now moving on to the C and D matrices, the sensor equation YAE is augmented by this new term DAW times W tilde G, and the resulting vehicle equation of motion is given in equations 5.11 and 5.12, where once again we have the new terms due to gust. Our closed loop system is given in equation 5.13. Now our A bar V is the same as the previous closed loop analysis because gust is an external disturbance. So the gust contribution does not affect the stability of the vehicle model. It just affects the disturbance. So if you have a gust disturbance, that will perturb the model, but then the stability of the model remains unchanged. So our B bar VW is now given here. Next, let's talk about the spiral characteristics of the gust column that we mentioned a few slides back. Now the gust column, QHG of I omega, is the generalized aerodynamic forces excited by the frequency domain sinusoidal gust, e to the I omega times x minus xg naught over v. Now if we apply the inverse Fourier transform to the sinusoidal gust, we get delta of t minus x g naught over v. So this is our traveling Dirac delta function. So this term, e to the minus I omega, in the time domain is a traveling Dirac delta function. Now in fact, the gust column is the frequency domain aerodynamic gust transfer function. So you can see when x minus xg naught is relatively large, the phase of the gust column changes rapidly with the reduced frequency k. So this x minus xg naught term here, if it's large, you can see that a small change in omega and remember omega corresponds to the reduced frequency k. A small change here yields a large change in this term. So this will exhibit a spiral shape at high frequencies when the term variation with k is plotted in the complex plane as shown by the Sears function over here at the right. Now, accurately fitting such a spiral shape into the RFA is not an easy task. So you can see from k0 to 2, we have a nice kind of well-behaved curve. But now as we keep increasing k, you can see that we're developing this spiral term. So when x minus xg naught is large, essentially, if it's small, we need k equals 10 to get to this spiral shape. But if x minus xg naught is large, you may only need k equals 1 or 2 to get to this spiral shape. So that's why it's important to keep x minus xg naught small. So next we have the GUST-Lag RFA method in ZAERO. So we developed a new strategy for the rational function approximation called the GUST-Lag RFA method. And this is developed to circumvent the problem associated with the RFA for GUST. So first, with the selected number of aerodynamic lags nr, the modified minimum state method is applied to QHH and QHC as before. Then a separate RFA step is applied to QHG, except that different aerodynamic lag roots nRG, denoted as RG, is allowed, which renders a different RFA for GUST, shown here. So this is our GUST term. Now combining the above two equations gives us this equation. So you can see that the normal mode and control surface modes are separate from the GUST modes. The GUST has their own terms. Now the GUST-Lag RFA method increases the number of aerodynamic states from NR to NR plus NRG. This gives more freedom to the RFA to achieve a better least squares fit for the GUST column, and it can be shown that the procedure to construct the state space equation using the GUST-Lag RFA method is nearly identical to that of using the modified minimum state method. So continuing our state space equation here, we now define D star as a combination of DHH and DHG. E star is a combination of EHH, EHC, and EHG, and R star is a combination of R and RG. Then the augmenting aerodynamic state vector is modified as shown here, and the state space equation of the aeroelastic system can then be derived as shown below. So our new AE matrix is shown here, where we've now replaced D and R by D star and R star, and our BAE remains changed, and then our BAW is the B term for the GUST. So next we'll look at the frequency domain approach of ZAERO. The frequency domain equation of motion of the aeroelastic system is given in equation 5.16. And you can see this is analogous to the state space matrices from before. So our AAE is given here in 5.17. BAE is shown in equation 5.18. BAW, the GUST term, is given in equation 5.19. And then our XAE states are made up of Kc and I omega times Kc, which corresponds to Kc and Kc dot from the time domain analysis. And our UAE is delta, I omega times delta, and minus omega squared times delta. The frequency domain outputs of the aeroelastic system are given next for the acceleration sensor. The sensor output can be derived from the second block of rows in equation 5.16, 5.18, and 5.19 to give us YAE here in equation 5.20. The state space equation for the sensor can be expressed in the following general form, equation 5.21. So we have y is c times x plus d times u plus this CAW times WG for the GUST. Continuing, The frequency domain plant model combines the equation of motion of the aeroelastic system and the state space equations of the actuator model. So in equation 5.22, we now have our new subscripts P denoting the plant model. So this is a combination of the aeroelastic model, AAE, and A actuator, our actuator matrix. So this is our new A, B, and C matrices. Our state vector has now been augmented with the control surface states delta, I omega times delta, and minus omega squared times delta. And our U for the plant is now the actuator inputs. Continuing, the frequency domain closed loop model is obtained by combining the plant model and the state space equations of the control system, and then closing the loop by the gain matrix. So equation 5.26, we now have our vehicle model. So our A bar V is given in equation 5.27. B bar VW is given by equation 5.28, where you can see where this incorporates the GUST input, and then AV is given here, BV, CV, and DV. And now our XV plants for the vehicle model are made up of our plant states and our control system states. Now equation 5.26 can be recast to solve for XV of I omega. So we have I omega minus A bar V of I omega inverse times B bar VW of I omega times WG of I omega. Now equation 5.31 is solved for XV of I omega starting from omega 1 equals 0 and then incrementally increasing omega by delta omega, where delta omega is the frequency step, until the predefined maximum frequency is reached. After we have x in terms of I omega, we can then apply the inverse Fourier transform, which yields the time domain state vector xv of t. So xv of t is just the inverse Fourier transform of xv of I omega. Now, there is a singularity in the frequency domain approach, which we need to take a look at. The frequency domain approach for the discrete gust analysis does not involve the rational function approximation. Therefore, it is the most accurate approach. However, the matrix in equation 5.31 is singular if plunge, side translation, and or the roll rigid body modes are included in the aeroelastic system. Now to show this, let's consider an open loop aeroelastic system with a plunge mode given by equation 5.33. So for the plunge mode, because KHH is 0, that term is here, and then QHH of 0 is also 0, you can see that this term will give us a 0. So the matrix I omega minus A bar V of I omega in equation 5.31 is singular when omega equals 0. However, because x dot v of t is the inverse Fourier transform of I omega times xv of I omega, and x double dot v of t is the inverse Fourier transform of minus omega squared times xv of I omega, the velocity and acceleration of the state vector are not singular at omega equals 0. So this omega term here just makes this whole thing 0. So next we have the hybrid approach. The hybrid approach establishes a time domain state space model without performing the rational function approximation to the spiral gust column turn. And the Fourier transform of the gust profile, as shown in WG of I omega, is first multiplied by the frequency domain gust column. Then the inverse Fourier transforms are performed to equations 5.6 to generate the time domain generalized gust excitation vector, as shown here in equation 5.36. So we have the gust terms solved in the frequency domain. We then perform the inverse Fourier transform to give us the gust as a function of time. Then the term B, AW times WG in equation 5.8 is replaced by the right-hand side of equation 5.36 to give us equation 5.37. So the first two terms, AAE times XAE plus BAE UAE are just the normal aeroelastic matrices that we saw before, and then this is our new GUST term. Now the acceleration sensor is given by equation 5.38. So we have this new term here for the GUST, and this leads to the closed loop state space equation 5.39. So we have our new, this is our excitation term due to GUST, B bar hybrid times the inverse Fourier transform of QHG of IK times WG of I omega. And this B bar hybrid is very similar to B bar VW in equation 5.13, except the BAW is now replaced by this matrix. We have the ZAERO matrix, and then Q infinity over V times M bar inverse and 0. So the summary of the three approaches that we have available for discrete gust analysis: the frequency domain approach is given here, where our xv of t is the inverse Fourier transform of xv of I omega, x dot v is the inverse Fourier transform of I omega times xv of I omega, and then x double dot v of t is the inverse Fourier transform of minus omega squared times xv of I omega. And this term here, I omega minus a bar v of I omega, is singular at omega equals 0 if rigid body modes are involved. However, we have special treatment developed in ZAERO to circumvent the singularity, and the frequency domain approach is employed by MSc Nastran. So one thing to note, if you have rate sensors or acceleration sensors, the singularity is not a problem. But if you have displacement sensors, that's where the singularity is a problem, and it's not possible to recover that displacement sensor due to the singularity. Next, we have the state space approach. This is the we need accurate rational function approximation of the GUST column. However, it's difficult to obtain because of the spiral behavior of the GUST in the frequency domain. So ZAERO employs the GUST-Lag RFA method to circumvent this problem. And we have only two inputs: gust velocity and acceleration are added to the state space equation. And this is suitable for gust load alleviation control law design. And then lastly, we have the hybrid approach. This only requires rational function approximation to construct a bar v. The time domain gust forces are obtained by the inverse Fourier transform, and the number of inputs is the number of modes. So next we'll look at the dynamic loads recovery, because if you're doing a gust loads analysis, you obviously are interested in what the loads are on the aircraft. So the major purpose of the discrete gust analysis is to compute the dynamic loads in the structure, such as forces and moments at structural degrees of freedom, and or sectional loads such as wing bending or wing shear. Now, to recover the distributed dynamic loads from the state vector, it's required to first remove the pre-multiplication of the modal matrix from equation 5.1 and then rearrange the resulting equation as shown here in 5.40. So now we're solving this in the modal coordinates, but then by only pre-multiplying by kgh, you can see that we have the force available at each grid point. So kgh is kgg times ph, mgh is mgg times ph, mgc is mgg times pc, and cgh is cgg times ph. And now this agh is just our AIC matrix times the spline matrix times ph. The AGC term here is the AIC matrix times the spline matrix times pc. And AJG is the AIC matrix times phi g of ik. And the subscript j denotes the number of aerodynamic panels. We have two methods available to recover distributed forces. The mode displacement method uses the left-hand side of equation 5.40, and the summation of forces method uses the right-hand side of equation 5.40. So with the mode displacement method, you can see we just have kgh times kc. So when we have kc is available, so if we just take our kc as a function of time, pre-multiply by kgh, that will give us the forces using the mode displacement method. The summation of forces method, we take the right-hand side. So we have c double dot, delta double dot, c dot, c delta, and our gust terms. We calculate all of this out, and that will give us our forces on the grids. So to review here what the FAA has to say about this, section 8.3, extraction of loads and responses, and then 8.3.2, a variety of methods may be used to obtain physical structural loads from a solution of the modal equations of motion governing gust responses. These include the mode displacement method, the mode acceleration method, and the force summation method. Next, section 8.3.3, the mode displacement method is the simplest. For converged results, the mode displacement method may need a significantly larger number of modal coordinates than the other two methods, and we'll see that. 8.3.4, in the mode acceleration method, the dynamic load response is composed of a static part and a dynamic part. The static part is determined by conventional static analysis, including rigid body inertial relief. Now, since the static part is determined completely and independently of the number of normal modes carried, adequate accuracy may be achieved with fewer modes than would be needed in the mode displacement method. And then lastly, 8.3.5, the force summation method is the most laborious and the most intuitive. In this method, physical displacements, velocities, and accelerations are first computed by superposition of the modal responses. These are then used to determine the physical inertial forces and other motion-dependent forces. Finally, these forces are added to the externally applied forces to give the total dynamic loads acting on the structure. So we'll first look at the mode displacement method. The mode displacement method computes the distributed forces F of t at the structural degrees of freedom simply by equation 5.43, where we have F of t is kgh times c of t. Now, the inaccurate modal solution of the plunge, side translation, and roll modes due to the singular matrix at omega equals 0 does not affect F of t, because the rigid body modes cannot produce internal loads in the structure. And this is evident that that the columns associated with the rigid body modes in the KGH matrix contain all zeros. The mode displacement method might be inaccurate if concentrated forces are involved, and the most severe problem of the mode displacement method is that it gives zero forces at those structural degrees of freedom at which no mass is attached to the finite element model. This is because in equation 5.44, kgg times ph can be represented as mgg times ph times omega squared, where this omega ni is the ith natural frequency. Therefore, kgh is mgh times omega n squared. So if a degree of freedom has no mass, its associated rho in mgh contains zeros, which gives zero force by equation 5.43. Next, we have the summation of forces method available in ZAERO. The summation of forces method calculates the distributed forces by summing all terms in the right-hand side of equation 5.40, which is given by equation 5.46. So F of t is the forces due to aerodynamic forces minus inertial forces. Fi of t is the inertial force vector given by equation 5.47. So we have mgh times c double dot plus mgc times delta double dot plus cgh times c dot. And Fa of t is the aerodynamic force vector. Now for the frequency domain approach, this can be calculated by equation 5.48. So we take the inverse Fourier transform of our frequency dependent terms and then pre-multiply by the spline matrix and then multiply by the dynamic pressure. For the state space approach, we have equation 5.49. So we have our c dot, c double dot, delta, delta dot, delta double dot, and then our gust terms, and then our aerodynamic lag terms. Now AJH, AJCI, and AJGI are obtained by applying the RFA to the frequency domain distributed aerodynamic forces. And then lastly, for the hybrid approach, it's mostly the same except for the gust. We now replace this AJG0 times WG over V plus L over V times AJG1 times W dot G of T over V. We replace that by the inverse Fourier transform of AJG of I of K times WG of I omega over V. So we'll review the load mod card, which is the component loads definition. This defines the load mode as a set of structural grid points for computing the component loads. So we have LID is the identification number. Label is the type of loads. So it can either be X shear, Y shear, or Z shear to measure shear force along the X, Y, or Z axis, or it can be X moment, Y moment, or Z moment for bending moment about the X axis, Y axis, or Z axis of the coordinate system CP. So CP is the next field. This refers to a Chord 2R card. If CP is 0, then the basic coordinate system is used. Next we have set K, which is the identification number of a pan-LST cards, which define the aerodynamic box IDs. And set G is the identification number of a set 1 or set add. Bulk data cards used to define the structural grid points. Now, if the mode displacement method is used, then only the set G field is used. Because remember, in the mode displacement method, we only use the modal coordinate time history to calculate the forces. So we just pre-multiply by the KGH matrix. For the summation of forces method, both set K and set G fields are used because then we directly integrate the aerodynamic forces among the boxes. So for the summation of forces method, we need the box definitions. So our recommendation when setting up the load mod card, for example, if you're going to do wing bending, is define both the set K and set G fields properly so that the set K refers to all of the aerodynamic boxes on the wing, and then set G refers to all of the grid points that make up the wing. This way, you can choose either the mode displacement method or the summation of forces method and refer to this load mod card, and you will get the proper answer. Now it's important to note that all of the structural grid points associated with the component should be included in the set cards. If, as we just said on the previous slides, missing structural grid points that have attached mass can lead to incorrect inertial loads. So for the set G, you do not want to refer to the same set 1 that is used for the spline. Remember, for the spline, you want to use a reduced set of grid points. But for the load mod card, you want to refer to all of the grid points that make up that component. And that concludes section 5.